We're continuing to look at phase change substances. In this video, I want to show you how to quantify values for specific internal energy. Also, I'm going to define a new property called enthalpy that we'll use later. But the big idea here is to get practice in learning how to quantify numerically values for internal energy, depending on what phase you're in. So you've got different methods of quantifying internal energy depending on the phase. So here we go with internal energy and enthalpy. So let's recap what you know about internal energy now. And I hope that you say, well, which one do you have in mind, capital U or little u? So let's remind ourselves what we have. You've got capital U, which is the extensive property version of internal energy. And little u is specific internal energy. And so that's, of course, going to be little u is capital U divided by m, the mass of the closed system, for example. And one thing in jargon, a lot of practicing engineers, many instructors, professors, simply refer to little u also as simply internal energy. And we do that as a shortcut. So you're just going to have to live with us on that, but do recognize that little u is formally is specific internal energy, and that's the intensive property version of internal energy. Units are going to be kilojoules per kilogram and or BTUs per pound mass. And so recognize that values for little u are tabulated in the property tables, not capital U. Okay. Oh, and I see in my little yellow text box, it just caught my eye that it says little u is nearly always called internal energy. Now what I need to do is throw a new definition at you, and it's called H, enthalpy. Now, we rarely use capital H. I cannot think of a single problem that I've ever had that involved capital H, or in other words, the extensive property enthalpy. And I think that might be the reason why we practicing engineers, many instructors, many professors refer to little h, the intensive property version, as simply as enthalpy. And so here's the functional definition that you're going to use. I'm circling here. Little h is equal to little u plus p times little v. H is U plus PV, and that's the definition of enthalpy. And instead of getting down in details of why are we defining this new property, I'll just tease you and say, look, we're not going to really use enthalpy a great deal until we start into analyzing open systems. And there's some engineering reasons why we need to define a new property called enthalpy. And so it says in my note here, it says there are certain processes where H, enthalpy, will be very handy instead of using U, internal energy. And I'd say by far and away, the certain processes would refer to processes involving open systems. Okay, so anyway, the other part is do recognize that little h, we often call it enthalpy. It's going to have, let's look at units. You see that since h is U plus P times little v, h is going to have exactly the same units as U, kilojoules per kilogram and or BTUs per pound mass. Well, why? So other than just saying, well, just trust me, I'm defining this. Why do we need to learn how to quantify little u? Okay, well, here's the why. In your homework problems, you're probably starting to figure out that you're using the first law of thermodynamics, in this case for a closed system, over and over again. And in many cases, you're asked to find heat transfer, or you're asked to find some other result where you're using the first law. And you say, well, wait a minute, work out. I'm gotten pretty good at determining work out. That's capital W is m, the mass of the closed system, times the integral of PD little v. So you've gotten pretty good at that. And over on the right-hand side, kinetic energy term, yeah, I can find kinetic energy term, potential energy term, yep, I can find that. But delta U is it's gonna be m times, so delta U, look, I've got a typo here. Delta capital U equals m times delta little u, not capital U, m times delta little u, and that equals m times little u2 minus little u1 when we're going through process 1 to 2. So sorry about that. That should be little u, okay? And so the why is you're going to need value for phase change substances. You're going to need to find values for little u both at state 2 and at state 1. That's the way we're going to do that. And you're going to need to be doing this over and over and over again in your homework problem. So that's the why. I'm going to show you, I'm going to try to explain to you what you need to do to find little u2, little u1 for different phases of phase change substances. Sorry about that. Gosh, I should have caught that right there. Capital change in capital U is m times delta little u. Okay, let's refresh our, let's recap the PV diagram. It's so important. Recapping has some value. Here's our vapor dome for a phase change substance. So P on the y-axis, specific volume little v on the x-axis. Here's our vapor dome. You do realize that we've got different phases of the same substance, of a pure substance. And let's say H2O. I think my coming up example problem is going to be H2O, I believe. So you've got these different phases, 1, 2, 3, 4, 5 phases differently. So let's look at the easy one first. How would we quantify little u and or little h if you have a saturated vapor or a saturated liquid? You're laying somewhere on the vapor dome. Well, this is really easy. If you have saturated vapor or saturated liquid, well, all you have to do, if you're given the temperature, you're going to go to a temperature table. If you have the pressure, you'll go to the pressure table. But look at these column headings. It's right there in front of your eyes. Internal energy, little u, is tabulated for saturated liquid, U sub F, saturated vapor, U sub G. We just talked about the units, so we've got kilojoules per kilogram over here in SI. Okay, for enthalpy, in the case you need to find enthalpy, you might be a little more careful. Notice there's 3 columns here. So you're going to be using the left and the right column. And for right, well, I'll tell you about the middle column here in a minute. Saturated liquid, H sub F. Again, if you're given temperature, you just look up a number. Saturated vapor, a number lookup. The middle column where it says evap, HFG, numerically, that is simply the numerical value Hg minus Hf. And the reason that that's tabulated is basically to determine the change in enthalpy going from saturated liquid to saturated vapor, which is the boiling process. But let's not worry too much about the why for that middle column right now. Just recognize that if you have a saturated vapor or a saturated liquid, it is child's play to look up the numerical values for little u or little h. In other words, UF for saturated liquid, UG for saturated vapor. Let's say you have a phase of a superheated vapor. The phase of a superheated vapor. You're going to go to the next table down, which is the superheated tables for, say, for water. And notice here, so I've taken a screenshot out of the book rather than going all the way to the book and going live. Do you see that there are sort of blocks of tables listed within the superheated phase? Now notice here that they're arranged by blocks by pressures. So here is a block of pressures, 1.5 bar, 150 kPa. Here's a block of data for the pressure 3 bar or 300 kPa. Now, on the column side, on the rows, the left-hand column is temperature. And so for superheated vapor, it takes pressure and temperature. Those are two independent properties in the superheated zone. And so then you'd have to know your temperature, and then you'll just go along the intersection point to look up U or H at your pressure and temperature combination. So again, for phase change substances, you're looking up properties U and H, well, and V, in these property tables. These are lookup values. I hope that helps you understand. So there is a difference between looking up values at saturated liquid, saturated vapor, and now superheated vapor. Now we're going to go all the way to the other side of the vapor dome. Do you remember the compressed liquid zone, which is to the left of the vapor dome? Compressed liquid. That's a lot like tap water. And I want to chase you back to your textbook because I don't want to drag out the details in the video. Go to your textbook, chapter 310 and 310.1, and you'll see in the book, it explains that typically compressed liquids are considered incompressible liquids, incompressible fluids, okay? And it does turn out, so I'm just telling you it turns out that result, that when you have an incompressible liquid or solid, it turns out that the internal energy U is a function of temperature only. So in other words, U for any temperature and pressure is about equal to, see that little squiggly line, is about equal to U sub F, the internal energy of the saturated liquid at the given temperature. And the same is going to be true for enthalpy. So if you have a compressed liquid like tap water, and you know the temperature of that tap water, that compressed liquid, all you need to do is go back into your temperature table and look up U sub F or H sub F. That's important, and a lot of students get tripped up on this. And that's why I'm including this. This is a subtle point about compressed liquids. And it turns out that we engineers deal with compressed liquids a lot because we deal with tap water, river water, cooling water for a cooling tower, ocean water. All of those are examples of compressed liquids. And so we evaluate little u and little h at the temperature of that substance as long as it's compressed liquid phase. I hope that helps. And now the last thing we need to cover is what happens when we are underneath the dome. What happens when we are a saturated mixture? What steps would, if I needed to find U, let's say I had a first law problem and this was my state. So I needed, let's say that was state 2. State 2. So I've got to find U2 because I've got a first law problem and I'm trying to find heat transfer from state 1 to state 2, and there's my state 2. Here's the way you're going to get a value for internal energy. Step 1, determine the quality of this state, this red dot. Step 1, determine the quality. That's like a different exercise, isn't it? Previous video. The next thing you're going to do is, let's say you know the pressure. Let's say you know the pressure of this. You would go to your pressure table. Alternatively, if you knew the temperature, you'd go to your temperature table. But if you know one or the other of those, you've got to go to one of those tables, and then you will look up U sub G and U sub F. So these two, so visually, look how similar we are. So do you see that this VG and VF represent specific volume properties at those phases? VG at saturated vapor, the F at saturated liquid. So you're going to look up the corresponding U sub G, saturated vapor, and U sub F, saturated liquid. And then what you're going to do is basically apply the definition of quality to determine U. So you remember that X was a proportion of vapor mass divided by total mass. Well, you can show then that here's that proportion of saturated vapor mass times U sub G plus what's left over. So do you see that 1 minus X is basically the percentage of what's left over from X? If X is 0.9, you see that 1 minus X is 0.1, or in other words, 90% of UG plus 10% of UF. That's the way I remembered it. So I was not a good formula memorizer. So I got this expression for using quality under the dome because I can get it into my head. Some people will say, well, that doesn't show up in the book. Here's a formula given in the book, and that's okay. So U is also equal to U sub F, just plain old U sub F, plus X, the quality, times the quantity UG minus UF. That is a true statement as well. And if you dissect these, you will see that algebraically, these two expressions for internal energy are identical. So neither of us, whichever you choose to use, both of those, of course, give you the same result because algebraically they are identical. If in the future, in future weeks, when you need to find H, it's the same idea. Okay. And so this is the way, that I remember how to calculate internal energy and enthalpy when I'm under the dome, when I'm a saturated mixture. I hope that helps. I've got some worked out example problems and a little background. And so let's see. Remember, if you go to the example problems STEAM playlist, I've got 3 videos, Vapor Dome Compare 01, 02, and 03. And I see for this one, Vapor Dome Compare 02 is 3 worked out examples illustrating examples, almost like homework problems associated with calculating internal energy U. So I would recommend that you give that a try. I see that it's 35 minutes and there's 3 worked out examples. Okay, we've come to the end of this video on quantifying internal energy and enthalpy. In this video, we defined enthalpy, H. H equals U plus PV. That's something you've got to commit to memory. H is U plus PV. That's just it. It's a definition. I tried to show you how to look up values for U and H for phase change substances, and sort of the approach you take depends on the phase you have. And then for saturated mixtures, of course, you're going to use the definition of quality X to try to remember, I've got to write down UG and UF, but how do I combine those to get a numerical result for my U value? And so I hope I showed you like a little trick on how to, when you remember the definition of definition of quality X, that can help guide you in sort of remembering the formula needed to get to that final U result. Next up is interpolation. So in my examples in the videos, magically the numbers that I've selected magically showed up in the property tables. Well, in the real world, we end up with pressures or temperatures or both that are not explicitly listed in the tables. And that means you've got to mathematically interpolate between tabular entries to get the property value you're looking for. And so that's all about interpolation. And I've got a whole video purely and some recommended videos for you to look at that are dedicated to interpolation, an important skill that you're going to have and master quickly in this class. So there you go. I hope you join me for the next video on some tricks and tips on interpolation.